We're now going to start looking at our next topic, which is circular motion. We've talked a lot about objects accelerating so far this year. That's been kind of a key idea throughout everything we've done. But we've really mainly focused on the speeding up, slowing down types of acceleration. Okay, we've talked about objects in free fall. We've talked about objects accelerating down ramps, across floors, etc. But it's always been that speeding up, slowing down type of acceleration. We do have another kind though, and that is the changing directions part. So now we're going to look at situations where objects are traveling in a circle, or at least in part of a circle, and changing directions. Okay, so maybe it's a quarter circle, maybe it's a semicircle, it could be a full circle, but they're going to be traveling in some portion of a circle. And when they do that, they're undergoing the changing directions type of acceleration. And we call this kind of acceleration centripetal acceleration, and we'll talk about what that means in a second. Two very, very important concepts we need to know about objects traveling in a circle, and that is the direction of the acceleration and the direction of the velocity. So whenever an object is traveling in a circle, at any point in the circle, that object is always accelerating towards the center of the circle. Okay. So we see on our chart over here on our circle, an object is moving clockwise around a circle, and we see the vectors showing the velocity and the acceleration at various points. And we notice that acceleration is always inwards towards the center of the circle. In fact, this word centripetal, right, is a Greek word, and it means center seeking. Okay, so when we talk about a centripetal acceleration, which is the type of acceleration we have when an object's moving in a circle, it is center seeking, always going towards the center. The velocity, on the other hand, is going to be tangential. Okay, so if you remember from geometry class, a tangent line to a circle is a line that intersects the circle at exactly one point, something like that, although I didn't draw it perfectly. So that velocity is always going to be tangent to the circle. So as we're traveling around this circle, at any given instant, the velocity vector is tangent, okay, to the circle at that point, okay, like that, those two green vectors shown there. So conceptually, those are two really, really important ideas that we need to know about the velocity and acceleration of an object moving in a circle. Now that we have the conceptual pieces about the direction of the acceleration, we're going to start talking about the amount of acceleration, calculating the magnitude of the acceleration. And so there's two things that this acceleration is going to depend on. Okay, the acceleration of an object moving in a circle is going to depend on the velocity of the object and the radius of the circle. And what I typically think about when we're doing this is I think about driving on an icy surface and trying to turn. What's going to make it, or what's going to affect your ability to turn on an icy surface? Your speed is going to affect it, right? The faster you go, the harder it is going to be to make that turn. And the other thing that's going to affect it is the radius of the turn. If you have a really, really sharp turn, that's much more difficult to make on an icy or snowy road than a more gradual turn. And so these are the two factors that are going to affect the amount of acceleration we have when an object's traveling in a circle or part of a circle. One quick note before we go on and look at the equation. We're going to focus for now on objects traveling at a constant speed in a circle with a constant radius. Okay, the equation we're about to look at would still be valid if we weren't traveling at a constant speed or if we didn't have a constant radius. But what that would mean is our acceleration would be constantly changing. Okay, if we have a non-constant speed or a non-constant radius, our centripetal acceleration is going to be changing. We will look a little bit at changing speeds while going in a circle, so either speeding up or slowing down while also changing directions. We'll look at that a little bit later in the year, but we're not going to look at that right now. We're going to focus on constant speed and constant radius. So here we have the formula for calculating the centripetal acceleration, a sub c. That's just to distinguish it from our speeding up, slowing down acceleration that we talked about before. And it's given by v squared, where v is the magnitude of the velocity, which is the same thing as the speed, divided by r, which is the radius of the curve. Okay, so our centripetal acceleration is given by v squared over r. This is just another equation we have for finding acceleration that applies to that changing directions type of acceleration. We also have a way of calculating the magnitude of the velocity of an object while it's traveling in a circle, also known as the speed of the object while it's traveling in a circle. So this isn't going to be the average velocity. We know that if an object travels in a complete circle, its average velocity is 0. What we're talking about is the magnitude of the instantaneous velocity, or the speed of the object at any given time. And the way we're going to find that is thinking about its motion around the circle. So when an object travels around a circle one time, all right, the distance it travels is the circumference of the circle, which is 2 pi r. Okay, the time it takes, we have a special name for that. We call that the period. All right, we looked at that a little bit with the Spring Lab earlier in the year, but a period is the time for any repetitive motion. Okay, in this case, an object moving around a circle. And we symbolize it with a capital T. The reason why it's a capital T is to show that it's a time, but distinguish it from just any old T. We make it a capital to show that it's a specific amount of time. In this case, the time to complete one full circle. Combining those two things, we take 2 pi r, our circumference, or the distance we travel when we go around a circle one full time, divided by t, the time it takes to travel that distance, and we get the magnitude of the velocity, or the speed of the object as it goes around in a circle. We now need to clear up a really, really important misconception about objects when they're traveling in circles, specifically about the forces that exist when objects are traveling in circles. So we've said that whenever an object is traveling in a circle, all right, it needs an inward acceleration, a centripetal acceleration, to allow it to move in a circle. And we know from the forces unit that if we have an inward acceleration, we must have an inward unbalanced force. Okay, in order to make an object move in a circle, there has to be some force pointing inward, some unbalanced force pointing inward, causing that object to accelerate. However, think for a second about your experience, okay, with turning in a car. Okay, now I'm going to give you a very, very specific situation for you to ponder for 1 second here. I want you to imagine that you're on a school bus. Okay, there's our big yellow school bus, and this is you sitting on the one side of the bus. And the bus is coming up on a really, really big turn. Okay, so the bus is going, it makes a sharp left turn. All right, I want you to think about the motion or the experience that you have when that happens. All right, the bus makes that sharp left turn. However, you feel like you're being thrown out of the turn. Okay, you feel like you're being thrown to the right side of the bus. So when the bus makes a hard turn to the left, you feel like you're being pushed right. However, I've just told you that in order for you to make that turn, okay, in order for you to go around that turn, we need an inward force to generate an inward acceleration. Okay, so if we need an inward force, why is it that you feel like you're being thrown out of the circle? I want you to consider a few other situations in a second, and this is going to help explain it. So think about a few more situations with a car. Okay, you're sitting in a stationary car, and the car floors it to accelerate forward. In that situation, you, along with the car, are accelerating forward. But if you think about that experience, you feel like you're being pushed back into your seat. Okay, so you feel as though you're being pushed backwards, even though you're accelerating forwards. All right. Now let's think about a moving car that's moving forward that slams on its brakes. We know that that car is going to accelerate backwards. Okay. In order to slow down, we need an acceleration opposite the direction it's moving. But when that happens, if you've ever been in this situation and someone slams on the brakes, you feel like you're being thrown forward. And we experience the exact same thing with a car turning. All right. So a car moving forward makes a sharp left turn. It needs an acceleration inwards towards the center of the circle in order to make that turn, but a passenger is going to feel like they're being thrown out of the turn. So this experience is not unique to turning. Anytime we're accelerating in a car, we often feel like we're being forced in the direction opposite the acceleration. So why is this? The real reason has to do with Newton's first law. Let's go back to our school bus example, okay? You, along with the school bus, are initially moving forward. And the bus driver is going to turn the steering wheel, causing the bus to turn. And there's going to be friction between the bus and the road, exerting a force on the bus, okay, towards the center of that turn, making the bus accelerate and turn. You, however, don't necessarily have a force acting on you. So what do you want to do? You're just sitting there, okay? What do you want to do when the school bus turns? You want to continue moving straight, okay? And so it's not that you're being thrown out of the turn, it's that your body wants to continue moving in a straight line at a constant speed. It wants to maintain its state of motion. And when the bus turns, you have the perception that you are being thrown out of the turn. Okay? But in reality, you're continuing to move straight until you hit the glass or the person next to you, or you grab onto the seat, or something, some force forces you back into the turn and causes you to turn with the bus. All right? So this feeling, and it works too when we're thinking about speeding up in a car when we slam on the gas, or slowing down very quickly if we slam on the brakes. The idea is the same. In all those cases, you're trying to maintain your state of motion. It's a Newton's first law issue. Okay? So even though you feel like you're being thrown out, what it actually is you're trying to move in a straight line until you're forced in by something in the car, whether it's a seatbelt, the side of the car, whatever, forcing you back into the turn and causing you to make that turn. We have a name for this feeling, okay? It's so prevalent that we've actually named it. And the name for this feeling is the centrifugal force, which is different than centripetal. Centripetal is the actual force that we've talked about before, and the actual acceleration that we have when an object's going in a circle. Centrifugal means the opposite of centripetal. This means center fleeing. Okay, centripetal was center seeking. This is center fleeing. Okay, and it describes this phenomenon of feeling like you're being thrown out of a curve when the car turns. The real reason, though, comes down to Newton's first law. And so sometimes you'll hear people talk about a centrifugal force. This is often known as a pseudo force. It describes a feeling. It describes how you feel going through that turn. But there is no force pushing you out of the turn. Okay, there is this one little caveat about assuming a rotating frame of reference. We're not going to do that, but there is one very weird situation when that force exists. But for our purposes, there is no force pushing you out of the turn. The reason why you feel that way is Newton's first law. We're going to work through some conceptual questions now, starting with some basic free body diagrams. So we have a few situations where we want to talk about the velocity and acceleration of an object, all right, and what forces cause that centripetal, that inward acceleration. All right. So we have, in this first case, a ball tied to the end of a string swinging around in a circle clockwise. So we're going to get the velocity and acceleration at each point. The acceleration is always inward, so it's going to look something like that. Our velocity is going to be tangent, so that's going to look something like that. Now, the forces that are creating that inward acceleration, well, in the case of this upper one, we have tension in the string pulling inwards. We also, because it's a vertical circle, a ball being swung around vertically, we're also going to have the force of gravity. So both of those forces are going to combine to give us that centripetal acceleration in this case. When we get to the bottom of the circle, we still have tension going in, causing the object to have a centripetal acceleration. Gravity, which is still going down now, actually opposes that tension. And so it actually means that we need a greater tension inwards to create the same centripetal acceleration, because now gravity is working against tension as opposed to working with tension as it was in the first case. Moving on to our next situation, a car travels around a curve on a highway. Okay, we have an acceleration that is inwards towards the center of the curve at each of those points, and we have a velocity that is tangent to the curve at each of those points, something like those blue lines there. Now, what force is keeping us moving in a circle during these times? This one's a little bit tricky, but it's the same force that allows your car to speed up and slow down. It also allows your car to turn. And what I always think about is, think about an icy road. When you try and turn on an icy road, what ends up happening is, rather than turning and following the road, you turn your steering wheel and your car just goes straight. And the reason your car just goes straight is because we've taken away the force that keeps us moving in a circle. That force is friction. So in all these cases, we're going to have an inward force of friction that ultimately keeps that car moving in a circle. Lastly, the ball traveling around a frictionless funnel didn't give us the direction. We'll just say it's going counterclockwise. So at each of these points, our acceleration is inward, okay, and our velocity is tangent to the circle, always. Okay, the force that keeps it moving in a circle, we don't have friction, so it can't be that. But if you think about a funnel, all right, the walls of the funnel are slanted, and so this ball is actually being pushed inward by the angled normal force. So in the case of this ball, it's the normal force keeping it moving in a circle. All right, moving on to two more conceptual questions here. We have, in the first situation, 4 different cars moving at various speeds in circles with various radii, and we want to rank the net force acting on each of the cars. Since the cars are all identical, and thinking about F equals ma, our net force, which is just the sum of the forces, is only going to depend on our acceleration if they all have the same mass, which they will because they are identical cars. So we really just want to think about the acceleration of these objects moving in a circle, and we now know that that acceleration is v squared over r. So let's go through each situation and think about what our acceleration would be. So in A, it's going to be v squared over r, because our velocities and radii are just v and r. In B, it's going to be 2v squared, that quantity, over r, or 4v squared over r, because we need to square both the v and the 2. For part C, it's going to be 2v squared, again, that entire quantity, over 2r, or 4v squared over 2r, which would simplify to just 2v squared over 2r. And for D, we're going to have v squared over 2r. So we can see that this acceleration in D is going to be the least. So I'll say the acceleration of D is the least. That's going to be less than the acceleration of A, that's the second least one, which is less than the acceleration of C, all right, which again simplifies to 2v squared over r, and that is less than the greatest one, which is the acceleration of B. Okay, you probably could reason it out mathematically. The fact that it depends on the velocity squared, so doubling that velocity term matters more than doubling the radius, but I think it's easiest to just do it algebraically. Moving on to the second one, a car travels along the track it's shown. We want to, at each point, we want to indicate whether or not the normal force is greater than, less than, or equal to the force of gravity. So, at point A, we have the force of gravity, and we have the normal force acting on this object. We know, since it's traveling in a circle, all right, going up and over that hill like that still represents a circle, so it's accelerating down. So at A, all right, the force of gravity is going to be, or the normal force is going to be less than the force of gravity, because we need more downward force to create that acceleration. At point B, this is a car on an incline. So we have our normal force here. We have Fg going straight down, and we typically break it into its components. So we can see, and this really is just a throwback to some of our incline stuff, that the force of gravity is going to be equal to Fg cosine of theta, which means that it's less than, once again, the full force of gravity. All right, so for part B, it's going to be less than. And then for part C, we have our normal force going up, we have our force of gravity going down, and this one now is accelerating up. Okay, once again, going through this valley does represent traveling in part of a circle, and we need an upward, and in this case, inward acceleration to do that. And so the normal force must be more than the force of gravity, or greater than the force of gravity, in order to create that inward force and therefore that inward acceleration.